Okay, yeah, so CanESM Ocean, you can see our core ocean group right now is quite small, but I've listed a number of people who've made important contributions in the past and moved on to other things, and a few people like Clint who designed a lot of the supporting infrastructure, and we'll talk about that next. And I would like to introduce Natasha Ridner and Jeff Stanley, who are ocean-related research scientists who have just started within the last month or so. So hopefully we'll make important contributions in the future. So this is a history slide that Neil already showed, so I don't want to belabor all the details. I just want to point out here that our adoption of NEMO as our ocean model is actually really recent. So CanESM 5 is really the only CCCMA climate model that uses the NEMO ocean. So we started working with NEMO about 10 years ago. And just to go, without going back into the very early history, so let's just go back to CanESM 1, which Jason and Vivek and Neil talked about as well. But CanESM 1 was our first model with biogeochemistry. So it had both the land carbon and the ocean carbon. So we introduced this ocean biogeochemistry model, which we called CMOC, or Canadian Model of Ocean Carbon. And then CanESM 2 basically had the same ocean biogeochemistry model, but a significantly improved physical ocean model, which had greater vertical and horizontal resolution, and a bunch of new parameterizations like KPP mixed layer physics and things like that. And it was Bill Merrifield was the main person responsible for implementing that. So I'll jump ahead one slide and just show you the difference in vertical resolution, right? So you see the L29, CanESM 1 had 29 vertical levels, and you can see the resolution is very coarse. I'm only showing like the upper 500 meters here. So in CanESM 2, we went to 40 levels, and you can see most of those additional 11 levels were in the upper couple hundred meters. So this is really good from a biogeochemistry point of view and from an air-sea interactions point of view. And CanESM 5 is quite similar. It has 45 levels rather than 40, but it's not a dramatic departure. CanESM 6 will have even higher vertical resolution. But so CanESM 5 was our first NEMO-based model. And this was our CMIP 6 contribution. And it also involved the introduction of a new biogeochemistry model, which we call CANOE, for Canadian Ocean Ecosystem Model. So in CMIP 6, we have two Earth system models, CanESM 5, which is CMOC, and CanESM 5 CANOE, which has the same physical climate, but different ocean biogeochemistry. And we also added oxygen to CMOC as a downstream tracer, right? Which is, so CanESM 1 and 2 version of CMOC did not have oxygen, but now oxygen, it is a prognostic tracer in the model, but it doesn't feed back on anything else in the model solution. So that's why I call it a downstream tracer. And but in CANOE, the oxygen does actually feed back on other processes in the model. And then CanESM 6, we are transitioning from NEMO 3.4 to NEMO 4.2, but this model is not yet publicly available. So in CanESM 5, the in-house parameterizations in the physical ocean, these were developed by Oleg Senko, with also contributions from Bill Merrifield, Warren Lee, and Duo Yang. One is Lee wave mixing, which means that eddies in the ocean generate gravity waves, which can break even hundreds of kilometers downstream, and this really alters the distribution of diapicnal mixing in the interior ocean. And then there's a latitude-dependent eddy mixing length scale, which is, so these are like the GM coefficients. These are the Jen McWilliams, the long isopycnal stirring coefficients. And so the length scale of that varies with latitude in a way that's a little bit different from theory, but anyway, you can read the papers. So Oleg has published papers on these parameterizations, and these are our main, like I said, in-house parameterizations in CanESM 5. But there's lots of other parameterizations that are included in NEMO, and users can choose their own preferred options, right? So for mixed layer physics, there's like 3 or 4 different options. So if you want to work with CanESM 5, you don't necessarily have to use the same ones that we did in CMIP 6. it really depends on what your scientific application is. So this is from the model description paper led by Neil from 2019. So this is the zonal mean full ocean depth, temperature, and salinity from Canius M5. And then the right-hand column, we have the deviation of those fields from the observation-based climatologies. And so if you wanted to summarize the bias in the model in a quick take-home, it's that the thermocline is too warm and the abyssal ocean is too cold. So that's the main most visible bias in the physical ocean model solution. So in ocean biogeochemistry, we have what we call the four pillars of ocean carbon chemistry are DIC, alkalinity, pH, and PCO2, right? So observationalists will say, well, you can measure any two of these and calculate the other two, but in the model, really, it's the DIC and the alkalinity are the carried tracers, and PCO2 and pH are diagnostic quantities. So DIC is CO2 plus carbonate and bicarbonate ions. So there's a lot of carbon dissolved in the ocean, but very little of it is actually in the form of dissolved CO2 gas. So we talk about DIC and CO2, or we kind of treat them interchangeably, or people will talk about surface flux of DIC rather than CO2. Now, in terms of the biological sources and sinks, this is where the models really start to diverge. So all the carbon chemistry, gas exchange, solubility of CO2 and oxygen is the same in CMOC and Canoe, but the biological sources and sinks are very different, right? So CMOC is what you call an MPZD model. It's really like the simplest model structure that you can have with prognostic biology. So there's a lot of processes like nitrogen fixation and iron limitation that are really highly parameterized, right? So Canoe is a much more complex ocean model. It has 19 tracers instead of 7, so it's more expensive. It has a prognostic iron cycle. It has multiple phytoplankton groups with variable elemental ratios. It has multiple size classes of detritus that sink at different rates. So basically, there's a lot of processes in the model that are really highly parameterized in CMOC that are represented explicitly in Canoe. So some of the scientific issues that we address with these models are changes in ocean circulation and ventilation associated with climate, trends in ocean acidification and deoxygenation, ocean atmosphere feedbacks, loss of sea ice, changes in greenhouse gas sources and sinks, primarily CO2, but we're looking at N2O as well. Geoengineering schemes like ocean iron fertilization, and prediction and predictability. So for example, here in British Columbia, the weather is very much affected by ocean atmosphere interactions in the tropical Pacific. So this is just an example of the ocean model output. This is ideal age, which is something you can't really measure in the real world, but in a model, it's easy to calculate. This is the age of the water since last contact with the atmosphere. In this case, at a depth of 1,000 meters. So you can see that the age of the water in the North Atlantic is much younger than at comparable latitudes in the North Pacific. And you can also see this signature of recent ventilation in the mid-latitudes of the Southern Ocean. But the North Pacific, of course, the water is very old. I don't want to say stagnant, but it's the oldest water in the world ocean since last contact with the atmosphere. So you can see that along the continent here and up into the northern North Pacific, there's this sort of shadow zone where the water is very old and it's very low in oxygen. So this is what we call the North Pacific oxygen minimum zone. And these regions along the west coast of North and South America, these are called eastern boundary currents. So at the eastern boundaries of the ocean gyres, there is very strong upwelling and a lot of productivity, a lot of organic matter sinking down and remineralizing, which results in these oxygen minimum zones. So I'll come back to that in a minute, but let's just look at the anthropogenic CO2 uptake. Okay, so this is in the CMIP6 historical experiment, which is the model description paper that I led in 2022. And so we have an observation-based estimate of the cumulative uptake to 2014 here in black. And then you have all the CMIP6 models in gray with the model ensemble mean being the thick line. And then in red and blue are two CMIP6 contributions. So you can see they're pretty similar. They're well within the range they're both models are biased a little bit low compared to the observations or the ensemble mean, which probably has to do with the relatively weak meridional overturning circulation. So going back to the North Pacific oxygen minimum zones. So here we're looking at the total volume of ocean with an oxygen concentration of less than 6 micromolar or less than 60. So 6 is the threshold for denitrification. This is where bacteria start using nitrate instead of oxygen as electron acceptor. And 60 is kind of a benchmark for the impacts people that like higher organisms like fish, they don't like less than 60. And for reference, a surface ocean that's in contact with the atmosphere would be between like 200 and 400, depending on the temperature. So ventilation of the interior ocean, particularly in the Pacific, is something that models don't necessarily do terribly well. So we're looking at this total volume of low oxygen water. And so again, we have observations in black, R2 models in red and blue, and then the whole suite of CMIP6 models. So, on the whole, we do pretty well compared to other CMIP6 models. By this metric, Canoe does a little better than CMOC. And then we go down to the 60 micromolar. And, again, we're at the low end. We're doing pretty well compared to the whole crop. But CNRM is a really interesting case. That's another NEMO-based CMIP6 model. And you can see that they're the lowest and closest to the observations for less than 6 micromolar, but for less than 60, they're the highest by far. So they're actually doing a very good job of ventilating the very, very low oxygen waters along the eastern boundary currents. But the North Pacific as a whole is actually weakly ventilated in that model. So this is DIC, again, dissolved organic carbon. This is the total amount of CO2 dissolved in the ocean waters. And here we're showing Taylor diagrams. I'm assuming people know how to interpret Taylor diagrams, although I'm aware that not everybody does. But these are for depths of 100 and 400 meters. So basically it shows the spatial pattern correlation of the spatial distribution of DIC on these two depth horizons. And in the paper, we have deeper ones as well. But let's just focus on the shallow ocean because this is really interesting. Okay, so again, we have CMIP6 models in gray with the model ensemble mean being the big dot. R2 models here, they're kind of well within the pack. They're not that different from each other. But when we include CANI-SM2, we see that the skill really increased markedly between CANI-SM2 and CANI-SM5. So this is a really interesting experiment because we have two models with the same ocean biogeochemistry but different physical ocean, and then we have two models with the same physical ocean but different biogeochemistry. So you can see between CANI-SM2 and CANI-SM5, you see a really marked improvement in skill, which is entirely due to the physical ocean, and particularly to the ventilation of those shadow zones along the eastern boundary currents. So anyway, those are just some science applications, and now we'll just talk a little bit about the technical aspects of, what is in an ocean model. So, NEMO has an ocean model, which is called OPA for Océan Paralysé. A sea ice model, we use LIM2, but later versions use LIM3 or SI cubed, and a tracer transport model, which is called TOP. Now, this is really great because in NEMO, all this stuff is done for you and it's done in a consistent way. So you don't have to code up all the tracer advection schemes and so on yourself. All you have to do is say, I want to add this tracer to the model and I want to use this particular advection scheme or this set of mixing schemes. And then biogeochemistry, well, Piscis is the native NEMO biogeochemistry. We don't use that. And then CMOC and Canoe are the ones that we developed in-house and embedded within this version of NEMO. So a biogeochemistry model, like I said, consists of carbon chemistry, air-sea exchange, biological sources and sinks, and external nutrient sources like aeolian mineral dust deposition and so on. And there's a set of scripts and tools developed in-house that are useful for visualization and interpretation. So runtime diagnostics, for example, are these global integral quantities, like what I'm showing here is the air-sea flux of CO2 or surface flux of DIC. And this is for CMEP6, a pre-industrial control run here in purple, and then the historical experiment here in blue. So the control run stays close to zero, and the historical run increases to about 2 petagrams per year of CO2 uptake as the emissions have ramped up over time. So these tools are available for visualization of the model output. So, how exactly does NEMO work? Well, there's source code, obviously. Every model has source code. It has a set of name lists and what's called an IODEF XML. I'll explain in a minute what that is. The file structures are a little bit different in the newer versions of NEMO, but the principle is the same. And then you have output files, which are like a grid T, a grid U, grid V, and then the PTRC files. That's the biogeochemical tracer files. These are all scalar quantities, so they're on the T grid. But the name lists set all of these different options that you can choose, right, for tracer advection schemes, for example, or mixing parameterization. So if you're going to work with NEMO, I think the first thing to do is just to get a copy of those name lists, print it out and read through it, because it's actually really informative. Some of the comments are actually pretty useful, and they will tell you what sort of options that are available to you to set these different switches within the models. So the IODEF is a file that just defines all of the outputs. So this is an example for the PTRC file, which, like I said, is on the T grid. So these are all the biogeochemical tracers. If you want to add a new tracer to the model, all you really have to do is just add one line to this file. Now, obviously, that's not all you have to do. You have to add a couple lines to the source code as well. But in principle, it is actually very simple and very user-friendly. So anyway, I'm almost done here. So take-home messages, CANIUS M5 is available for scientific research into ocean circulation and biogeochemistry in either coupled or ocean-only modes. The NEMO model is fairly user-friendly and allows rapid implementation of new tracers, and there are many different options for mixing parameterizations, tracer advection schemes, and so on. So just read the name list, familiarize yourself with those, and read the papers in the special issue, and that will hopefully give you some ideas about what sort of science applications you might find this a suitable tool to use. Thank you.
Thank you so much, Jim, for that talk. That was really informative and great. Does anyone have any questions? No questions. Okay. Paul, go ahead.
Yeah. I'll let Robert go first. Robert, if you want to ask, go ahead.
Hopefully you can hear me.
Yeah.
I was just curious.
Yeah, we can hear you.
Okay, great. Really great talk. The advice about the nameless, I think, is really great advice in particular. I was curious if there are plans to do sensitivity experiments with the ocean model and sort of testing what you can do by just tuning the parameters differently, kind of similar to what was done with the atmospheric model, if this was something that you guys had considered. Yes,
it is something that we're doing, maybe not quite in a systematic way as what John and Slava are doing with the atmosphere. But I believe there are a couple of ocean parameters that are included in that exercise.
Yeah. I don't know if that was the only question. Oh, that's mine.
Yeah,
yeah, so I guess my question is along a similar line to Robert. I mean, one of the things we're talking about here is, how easy it is to change the model. And when you change the ocean model, of course, in the coupled setting, if it's standalone ocean and I guess you're driving with prescribed atmosphere fluxes and so on, that might be kind of low risk. But if you start changing the ocean model a lot, I guess you can drift into new climate states. And I was wondering if it was more, I guess, along the same lines with Robert, but what the time investment involved in that is pretty extensive. So just curious, like, are there any sort of top experiments you think we should be thinking about for that kind of exploration?
Well, I mean, the one that we're experimenting right now with the transition from the NEMO 3.4 CANI SM5 to our new NEMO 4 based ocean model is this parameter called ETAU0, which has to do with the radiation of energy out the base of the mixed layer as oblique internal gravity waves. It's a default setting in NEMO, but it's a little bit of a dodgy parameter. I mean, I don't think it's a real process, but the fraction of the energy that it represents I don't think it's nearly that large in the real world. But yeah, we are experimenting with that. And yes, it does take a long time to equilibrate and be certain about the effects it has on the solution. It does have a pretty large effect. But I think what parameters that you would want to change, I think it depends on what your science applications are.
Yeah, that makes sense. Yeah, I think this is more food for thought for future workshops and tutorials and so on. Is what you should do, what you should change when you're moving to a new model configuration. There are some go-to parameters in the atmosphere. And I was kind of curious, like if you could build up a list of those for the different versions of NEMO as well. Food for thought for later. Okay, thanks very much, Jim.
Okay, thank you.
Okay, I'm just gonna stop the recording and then start again.